So just to remind ourselves of where we are within the arc of this particular case study, so far we've been looking at one of the key objectives that the company wanted to address, which is predicting when a spare part is required at the time an error message is generated, at the time a task is raised. In the next section, in the last section here, we're going to look at trying to order parts ahead of dispatching the technician out so that we can minimize delays. In other words, what we're going to do is try and focus in and say, can we actually estimate or make a guess as to what part is required, or even just whether what the outcome of that particular maintenance job is going to be, whether it's a reset, etc. And we're also going to focus on trying to identify sites which are likely to require another visit within 20 days, so sites which throw another error message within 20 days. And the organization was interested in trying to identify these sort of repeat offender sites, so that they could, be more proactive and take preventative action to stop that from occurring. So in this example, rather than focusing on one particular outcome, i.e. something like whether or not a part replacement is required, we're actually going to focus on a number of different outcomes. We know that when the field technician is sent out to inspect the site, that there are a number of different outcomes from that particular inspection and that particular maintenance job which lead to it being resolved. And we have some information about what the technician did at that point in time, because as we saw in an earlier example, we have the engineer response. And if you recall, we text mined that response. We cherry picked and classified and categorized the things that the engineer was talking about there, and we turned them into a series of flag fields along the side here, which we can see, such as whether or not an alarm was mentioned, whether or not that particular issue was related to an antenna. Here we can see it says replaced the faulty antenna, so that would be a part replacement and the antenna. We have other ones here related to cabling. We have filters. We have certain component parts like FSME and BCFA. And I've just made a little note here in the background. BCFA is a basic control function unit. FSME is a flexi multi-mode system module. These are particular components which need addressing or need replacing at particular points in time. Can we actually find a way to predict these outcomes at the time that the error message is generated, so that we can be much more proactive and maybe order parts ahead of the engineer being dispatched, or order parts so that the engineer can pick them up on site when he or she arrives to inspect that particular site. So what we end up with is a series of flags that we were trying to find rules or predictions for. We may not find rules or predictions for every single one of them. We may not find rules or predictions for vandalism or theft. I mean, some of these occur very rarely. As we can see, tuning issue only occurs twice. Some of them occur very commonly, like resets occur 27% of the time. Rectifier occurs 6% of the time. But some of them are relatively rare, somewhere in between. So FSME is coming in about 3.5% of the time, and BCFA is coming in about 5% of the time. So to do that, we need to choose a different type of algorithm, a different type of technique. We can't use a standard classification technique because there are simply too many outcomes. And instead what we do is we go for what's called an association technique. And an association technique is when you can take a whole bunch of fields and say, okay, these are going to be my input fields, and then choose a whole bunch of output fields and say, these are the things I'm interested in predicting an outcome of. So if I connect this up to the algorithm, you'll see here I've just called it outcomes. If I right click and browse it, you'll see that here are the things we are trying to predict. These are called the consequence. These are all the things that we've mined from the text of the engineer, whether or not it was antenna related or BCFA or battery related. And here are all the potential inputs, the site type, the main error code, and also the stuff we've text mined from the error message. So whether or not it was antenna related or cooling related. We've got a bunch of different fields we can put in here. We've got whether or not it occurred a weekend, whether or not the technology is GSM or UMTS, and the main site technology that's used there. And what we're going to try to do is to uncover a series of rules which might help us identify situations where it's much more likely that, let's say, a BCFA is going to be involved in the outcome of this particular job, or it's going to be a cabling related job, or it's going to be a job that simply requires a reset, for example. And to do so, all we got to do is once again click run, and that will go and generate very quickly for us a model. And this time, instead of seeing a decision tree when we look inside the model, what we're going to see is a series of rules in the form of what's called an antecedent, a before, and a consequent, an after, before and after series of rules. And the antecedents, of course, are going to be based simply upon information that we knew at the time the error message was raised or the job was created. If we click edit to look inside it, we can see that it starts off as a fairly simple table, and it's sorting the rules that we can see in order of confidence. So what we mean by this is how often that rule is correct. The confidence value is just a percentage times that rule is correct. And basically what we're seeing here is there's a main error code here coming as 7651. And 79% of the time when you get that error code, a part replacement is required. Now you might think, well, why don't I just use this instead of using a part replacement model in and of itself? Well, first of all, that error code only occurs 2.4% of the time. This is known as the support, so it only occurs fairly rarely, but when it does occur, there's a 79% confidence that a part replacement is going to be required. So this is particularly good at cherry picking or finding little rules and situations where there is an elevated likelihood of a particular outcome occurring. And I can ask it to throw in some more information here, such as a rule ID and the number of instances. So you can see there's only 83 instances here, hence 2.4%. And it's been given a rule ID of 9. You can see also that the model here has actually generated 583 rules. So one of the ways in which we use this algorithm is we have a lot of control over how strong a rule we want, how many rules we want to create, etc., etc. So what's interesting is as we look down through this, the next rule is basically a subset of the previous rule. It's saying, if it's 7651 and the site type is macro, then that's rule number 79. There are 78 instances of that, and you get a 78% confidence value. So it's really a subset of the previous rule. Here's one that includes this BCFA card, which, as we recall, only occurs in about 5% of occasions that's being mentioned. But it's saying that when you get a 7706 error code and the error message mentions O&M link failure, operations and management and link failure, the site technology is series 4, and the protocol it's using is UMTS. That's rule number 501. There are 72 instances of that. That's 2% of the data. But when that happens, 59% of the time you're going to require a BCFA card probably to be replaced there. And so on and so on. So we can actually scroll down through these series of rules, and we can see different consequences for different rules. So here's a rule for when a reset is required. Here's a rule for let's see, those are all resets and BCFAs to start with. Here's when it's going to be cooling related. We scroll down, there's a cabling rule coming up at this point in time. We start to scroll down through them. And we see part replacements, we see feeder related, we get power related. So there are different ways in which we can view this rule. One way to see it is by the confidence, but there's another way which is very commonly used in marketing and which is particularly useful here for identifying parts which are very rarely used, but where situations indicate that they have a much higher likelihood of being used than the baseline, and that is to call in what's called a lift value. If I call in a lift value here, I just need to stretch out these rules, give it a bit of room again, and I'm going to sort it by the lift value and then explain what's actually happening here. If I look at the bottom of the series of rules here, I can get down to lift values close to 1. If I get very, very close to 1, here's values which are very, very close to 1. See this value here of 0.99, a value here of 0.101. It's basically saying if it's a weekend, then chances are you're going to have a part replacement, and that's 24% of the time. Well, 24% of the time, parts are replaced anyway. So this rule is pretty useless because it's basically it's not telling us that there's an elevated or greater likelihood of part replacement, and hence the lift value is very, very close to 1. In fact, lift values less than 1 mean that it's a lower than baseline chance that will be the outcome. So we might go to the filter here and say, okay, I want you to filter out anything where the lift value is less than a certain point. So I could say, it has to be greater than, and I'll make it 1.5 here, just Just make it a little bit easier, click OK. That gets me down to 231 rules, and that's kind of much more useful now. So now I'm pointing it to rules where the lift value is greater than 1.5, and by that we mean that there is a much greater elevated chance of that outcome relative to a baseline. So in other words, if the lift value is equal to 2, you're twice as likely to see that outcome than you would randomly. And when we sort it in order of lift here, although the confidence value for FSME is only 59%, you got to remember that FSME is used comes up very, very rarely. And it's saying here, if you get an error code of 7651, you're 16 times more likely to require an FSME, which, as we know, is this Flexi multimode system module. Feeder related rules start to fire at this point. So here we have 15 times more likely to be feeder related. If there's a loss of signal attenuation, you're getting this error code, it's UMTS, and the site type is a macro site as opposed to a microwave site, and so on and so on. So as we go down through these, we can see where it's likely to be antenna related. Signal attenuation with this error code means you're 10 times as likely to be an antenna problem. So we can really start to predict what the outcome is, or a swapped component coming up here. We can really start to predict what the outcome is likely to be at the job level when we start to look at this approach. And if I just connect up a table at this point, and we'll look at what this particular model generates for us. If I scroll along to the end once again, here we have rules, and it's saying I've got a likely outcome. I think this one's going to be a reset. I think this one's going to be a part replacement. I think this one's going to be a BCFA. Of course, there are multiple potential outcomes. So in some situations, it says, well, if it's not going to, if there's a 28% chance it's going to be a reset, but there is a 21% chance it's going to be power related, and I don't have any other more rules. For example, here I think it's going to be power related, a part replacement, or a reset, and it's telling me the percentage chance, and I can get it to save 3, 4, 5, 6, 7 rules and get it to tell me, you know, what you think the likelihood is of this particular outcome resulting in a BCFA card needing to be replaced or a reset required, with the relative probabilities associated with that. And it aids the decision making of that business greatly, because now they can start to actually calculate what the likely outcome is of that job at the time the error message is generated. And that's very, very powerful. So in the next example, in the very last example, we're just going to jump to this problem of trying to identify sites where, even though the engineer has gone out to fix something and tried to address that particular problem, that nevertheless they have to return to that site within 20 days. And this is something that tends to be related to sites which are regarded as what they call repeat offenders. So I'm just going to finish up here and show you how we can address the third and final objective within the case study, which was identifying sites that will require another visit by an engineer or a field technician within 20 days of the previous visit. And we can actually look at the number of days until the next visit occurred at that site as a distribution, because that's something that we've actually recorded in the data. And what we find that this is a very skewed distribution, and that in fact the most common number of days elapsed before a site is required to be visited again, it's actually around about 3 days. So there's quite a lot of sites where they fail almost immediately. So the 20-day cutoff is entirely a arbitrary cutoff that the organization used for operational reasons. And in order to create that 20-day cutoff, really actually all you have to do is just slice this distribution and then ask it to go and generate what's called a derive node, or which will create a flag field for you of true and false. You just got to make sure that you slice it at about 20%. If I did that, it would create a little derive node for me, and I can just show you inside here that in fact it's just saying I'm going to create a new drive field here, which I'll call 20 days, just as illustration. And it says, I could set this one for, if it's less than 20, then make it true. If it's not less than 20, then make it false. Now, in fact, it's choosing 18 here because I roughly guessed it, so I just edit that. And that's how you create that field. It's really, really simple to do within the modeler application. So I've already created that field. And once again, I can just show you the data by putting a little data audit node on here. And of course, as we would expect, we've got quite a lot of fields we can work with. And the field that we're using, which is our target field, which is return within 20 days, where actually only about 8% of the time that occurs where a visit is required again within 20 days of a failure being issued. But they're very interested in trying to predict that. So this is something that's going to happen after the inspection has occurred, after the fix. So that means we can now start to make use of not just information regarding the error message that was elicited, but also the things that the engineer did and the amount of time it took to fix it, etc., etc. So again, because we're looking at a particular, very specific outcome, we would normally use a classification model. And in this case, I'm just going to use C5 because it's a simple way to show how we can address this. And in fact, this was the particular algorithm that we used on the project. So if I right click and just run that, as you can see, it's trying to predict return within 20 days. And what's of particular interest in here is what factors it's choosing to predict this outcome. So if I click and hit edit here, we can look inside it. And you can see that it's showing me a predictor importance chart here. So what's interesting is it thinks that the variable equipment type coded is very important. So that means that must occur a number of times within the model. And it must do a pretty good job of discriminating between sites that require another visit within 20 days and those that don't. The time to fix is important. Time to fix in minutes is important. Fixed temperature related issues, day since previous fix, whether or not a reset was required, the region type, whether or not it was antenna related, and some weather data coming in here. There's some equipment data in here, and some data referring to how long it took to fix it. So time to fix here, I think, is 18 hours. If it's fixed in less than 18 hours, it's saying that generally speaking, you don't need to revisit that. And if it's greater than 18 hours, you don't have to revisit it. But what's actually happening is that there's a slightly different subset of rules associated with fixes under 18 hours. It's saying if a BCFA card is needed, then you don't need to generally respond to that or return to it. 99% of the time you don't have to return to that. But if a BCFA card is not used and it's under 18 hours and it's a lock issue, then it's saying actually 30% of the time you do need to respond to it. Now it's a relatively small number of cases here, only 13. But if we go to the viewer window, it's probably easier to see. So you can see it's splitting here right away on time to fix and whether or not it's less than or greater than 18 hours. And what's interesting is if it does take more than 18 hours to fix it, it generally tends to get fixed and that they don't return within 20 days. In fact, none of those 166 records have resulted in a site needing to be revisited. The vast majority of records, of course, we've got 3,261, are less than 18 hours. And as we can see here, if it involves a BCFA card, they tend not to get revisited. There's 176 of those. We've still got 3,000 left here where a BCFA card was not required and it was under 18 hours. And now it's splitting into whether or not it was a lock issue. So maybe there's an issue with chronic vandalism, where the locks are getting broken, we need to come back to it. And then we've got things like previous mean 1 day temperature, and this is the average temperature, and this is based in a temperate climate. So an average temperature across a day of 22 degrees, that means it's a pretty hot day if that's the average temperature. So there are 48 cases where you got an elevated average temperature, and 26% of the time they needed another visit. So some of these systems are very, very sensitive to temperature. They have air conditioning units in it, and they struggle to cope when it gets hot. And then within those 48 cases, we have whether or not the error count was greater than 1 in the last 12 months, and that increases it to 34%. If it was greater than 1, if it was less than or equal to 1, then it's actually those 10 cases don't fall in that category. So now we get less than or equal to 22 degrees mean temperature, but again, whether or not the fix was temperature related, whether or not there was an error about a temperature spike at a certain point in time, or an issue with a cooling system. And it's starting to pull in, whether or not it was loop related, and if it was, it's only 2% chance that it's going to be revisited. If it wasn't, it's an 8% chance we'll go back to our baseline. Over here we've got whether or not it was a very dry day, so whether or not the previous precipitation was less than 10.7, I think that's millimeters or centimeters. If it was greater, then they all get revisited, but these are relatively small numbers, and so on and so on. So it's a very big model, but we can start to see, you know, as it starts to split out, what is the profile of specific sites which are going to need revisited within 20 days. And really what the model is saying is there's a range of different factors which are environmental, which are related to equipment, which are related to the nature of the fix. And as a result of that, it's a fairly complex model. It's not telling one story. However, if we want to assess how accurate the model is, well, once again, obviously this model is going to generate some probability values for us, which we could then score against every job after it's been completed and identify whether or not we're actually going to need to revisit that site again within 20 days. But if I just want to have a quick look at how accurate it is relative to a random baseline, if I put a gains chart on here and click include baseline, I'll just focus on return within 20 days is equal to true. And of course, as we know, 8% of the time the sites have to be revisited within 20 days. So what we're saying here is if we had a perfect model, we could find 100% of the sites that needed to be revisited within 20 days from 8% of the data. And if we were dealing with a random model, of course, we could only find 8% of the sites that needed to be returned within 20 days from 8% of the data, because it's entirely random. But using our model, we can see it actually starts to level off around about here, so it's doing very well. And we're saying that we can find 72% of the sites that need to be revisited within 20 days from 14% of the data. So that means there's going to be some false positives and some false negatives in there. But it's probably a pretty good start for identifying, you know, sites that maybe are going to be repeat offenders or have chronic issues associated with them, and it means that they can manage those sites proactively rather than waiting for an error message to be thrown again within 16, 14 or even 4 days. And that makes it quite a compelling application, quite a compelling way to approach this particular problem. I do hope you found that useful. If you'd like to find out more information about the Predictive Operational Analytics application template, or about the use of IBM SPSS Modeler software, then please do visit our website at Smart Vision Europe. That's sv-europe.com.